Today's lesson's over section 7.1, Modeling with Differential Equations. A differential equation is an equation which contains an unknown function and one or more of its derivatives. The solution to a differential equation is not going to be a set of values, but is going to be a set of equations. So here's some examples of kind of different setups that you might see for a differential equation. This one I wrote 3 different ways, just so the same one. So you can have the y prime or double prime, you could have the dy over dx, or you could have f of x prime and those kind of things, okay? So taking that first one, I want to be able to show that y equals e to the negative 3x satisfies the differential equation of y double prime plus 2y prime equals 3. And so first I would need to take that initial function that they gave me and find y prime and y double prime. Then from there, to show it, I just want to plug it in. So where I see y double prime, I'll plug in 9 times e to the negative 3x. For y prime, I plug in negative 3 times e to the negative 3x, and then y just in for the y. And then from there, I want to be able to simplify both sides. And if I get the same thing on both sides, then I've shown that it's true, okay? Now here, a common assumption when making a model population growth is that the population grows at a rate of proportional to its size. So here I have the differential equation of dp divided by dk, or dt, so the derivative of the population with respect to time is equal to k, which is a constant of proportionality, times the population. So they would like to show that one of the only equations that satisfies this differential equation is the equation of y equals c times e to the kt power. And c is an initial condition, like a constant or something, and k is that constant of proportionality. So here, like we did before, we want to be able to kind of take that derivative, but y is actually the population size that's representing the same thing over time t. And so I can insert in p for y, because they are the same, they're equivalent, and then I can take the derivative. So I get dp over dt for the left side, so p prime I could have written as well. And so that k comes down and moves out in front of the c times e to the kt, which, if we already said that p is equal to c times e to the kt power, that's really the same thing as p. So I can insert that back in and get my answer. Example 3 here is wanting us to show that every member of the family of functions of y equals 1 plus c times e to the t divided by 1 minus c times e to the t is a solution of the given differential equation. And so to do that for this one, like we did before, I need to take the derivative of y. And so this one, because it's division, I'll have to use the quotient rule. So remember the derivative of the top times the bottom minus the derivative of the bottom times the top, and then divided by the bottom squared. And so notice that we have some couple terms that cancel out after we distribute through, and then I'm able to get 2c e to the t divided by 1 minus c to the e, or cet squared. So now for the other side, if I actually plug in my y into that function, because there's a place for it, if I can get the same value, I've shown that this works. This is a solution for every member of that family. Okay, so here with a square, I can square the top and the bottom, and then that 1 on the right of the bracket, I will make common denominator, so that means top and bottom both get a 1 minus c times e to the t squared. And then I'll just FOIL those things out. So I'll FOIL out the first one, FOIL out the second one. Remember, there's a minus in between, so I'll have to distribute that negative through to that last parentheses. And here I have several like terms. It looks like I also have c squared e to the 2t. They'll cancel out, and the ones cancel each other out, leaving me with 4 up there, but then multiplied by that 1/2 out front reduces it down, so I'm actually able to get the exact same thing. And then example 4 ties in with example 3 using the same differential equation. They want to show that y of 0, meaning t, so y sub t is equal to 2. And so Anytime they add in that it's the variable that they're doing the function with respect to. So I want to be able to figure out what C is. So anytime they are looking for an initial condition, they want to be able to figure out what the constant is for that equation. So here I'm just plugging in 0 and 2 into this function to see what my C value should be, and I get 1/3. And so then I go back to the original, I plug that in. Now notice I'm going to have fractions in the numerator and denominator, so I want to make it so it's not a complex fraction. So I multiply both top and bottom by 3, and that allows me to get the following answer. Okay, have fun.